So in the last class, we have gone through the series RLC resonance part, and we have gone through what are the half power frequencies, how we can express them in terms of Q factor and all those things. But definition of the Q factor was not discussed. Let us quickly cover that part, and then gradually we move to parallel resonance. So here you can see the Q factor of a series RLC circuit is defined as the voltage magnification, we can call it. So what is that? It is actually the ratio between, just a second, Shriman, close the door. Okay, anyway, so we have series RLC circuit, and for that we want to define quality factor, which is the voltage magnification part. So how it is defined? It is the ratio between the drop across the capacitor or the inductor and by the drop across the uh, total voltage, I mean what you are applying here. So this is your RLC circuit, series RLC. This is VR, this is VL, this is VC, and this is your supply voltage V. So V is equal to what? During resonance, when I0 current is flowing through it, during resonance, V you are applying, and your current is in phase with V, right? Because this is the total, it is purely resistive during the series resonance, because this is what your VL, and that is equal and opposite to VC. So VC is equal to minus VL. Then what does it means? The input voltage or the supply voltage is equal to I0 into R. And what is your VL? VL is basically your J into omega into L into I0. So absolute value we can write it as I0 omega L. So if you put it here in place of VL0 by V, then you can get it like I0 into XL0. XL0 is nothing but omega 0 into, I forgot to mention omega 0, which is resonance frequency. So that omega L by R. So we can write it as VL0 by V, and that is equal to I0 into XL0 by I0 into R. We can also write I square XL0 and I square R, which is your active power, and this is your reactive power. So it is also the ratio between reactive power and the active power. That also you can call as a quality factor. So this is your Q when you take VL. So same thing will be for the VC0, because this is same voltage magnification, because VL is nothing but VC, which is equal to I0 by omega 0 into C. So if we write in that form, then we get Q to be equal to this. Okay. So quality factor is equal to omega L by R. We can write omega 0 by omega 0 into L by R. So here you can put omega 0 as 2 pi f0 when you know the frequency. So this is what, this is basically the phi is equal to the angle during the power factor. So you have the reactive, this is your active power component, which is I0R, I square R. This is your reactive power, I square x L0 or I0 square x C0, whatever it is. And this angle is your phi. So you can write it as, this is what, either it is omega L, omega 0 L, or you can write 1 by omega 0 C. So this is basically tan of phi. So cos phi is basically your omega L by Z, or 1 by omega 0 C by Z, and tan phi from there you can write, which is omega 0 L by R, like this. So which is equal to the quality factor. Okay, so cos phi is your power factor and tan phi is your quality factor, Q factor. Okay, so this can be also expressed in terms of maximum energy stored in the inductor divided by energy dissipated per cycle into 2 pi. How can you write this? This is basically your half L I0 square that we have learned, that in energy stored in an inductor, this is equal to half L I0 square divided by energy dissipated in per cycle is energy dissipation will be carried out only, it will be happening only at your resistive part, so there will be I square R loss. So I square RT is your energy, right? And how you can relate this T by pi, 1 2 pi by T is equal to your F. So that T you can write in terms of this. So 2 pi by T, if you write it as T equal to 2 pi by F, so you get this. Okay. Is it clear to you how you are getting this relation? Because
Yes.
how we are relating T, fine. So then you can say that quality factor we are getting the same value, and once you substitute omega 0 equal to root over LC, then you get the same expression, which is 1 by R into root over L by C in both the cases. So similarly, in case of the capacitive circuit, I mean, from the point of view of capacitive part where energy is stored in the capacitor, this is equal to half C into V0 square, and V0 is equal to I0 into XC. This is the drop across the capacitor. We should write it V0 C square here somewhere, or VC0 square anyway. So this is how you can get the expression of the quality factor once you do the adjustment of T as 1 by T is equal to F, and then in that way. Okay. Or if you want to write in terms of radian, then 2 pi by T is equal to your omega in that way. So this is the overall expression which I have already given. Now this is how you can write your half power frequency, which we have already seen in a last class once we have solved the equation. Just for the I don't think I have to again rederive it, because uh, it will be repetitive. Just verify this whether you can get the same expression or not. And this is what circuit current at frequency other than resonant frequency. So that if you would like to express in terms of resonant frequency and quality factor, that you can write like this: current at resonance, it is purely resistive, so it is I0 equal to V by R. And then current at other frequencies, you know, this is your impedance, so you can write it like this. Now what you are supposed to do here, if we just write like this: the current lags behind the applied voltage by a certain angle phi, which is your related to your power factor. That anyway we are not using somewhere here, but what we are trying to do, we are trying to find out the ratio between I by the resonant current I0. So if you do that, you are arriving at this, which is your cos phi. So this is your cos phi, and that you can write in terms of this, where if you take from here omega 0 L, if you just this term, if you rewrite like this, root over, in the numerator it is R, if you take R common, R square common, then you are left with 1 by omega L by R minus 1 by omega C R, that whole square. And what do we know? Omega 0 L by this is R by R is equal to your Q Q0. So we can write this as this part as Q0 by um, uh, this is sorry, it is Q0 into omega by omega 0 minus, it is again Q0 into the other way around, it is omega 0 by omega, isn't it? This part you can write like this, root over this R will cancel out. So what else we are left with? Here you can take q0 from both the part, you can take common, so you can write it as 1 plus q0 square divided by f by f0 minus f0 by f whole square, because f equal to 2 omega equal to 2 pi f, so we can write from here to here. So either you can write in this form in terms of frequency and the quality factor, uh, then you can write I as I0 divided by the whole thing, 1 plus Q0 square, then F by F0 minus F0 by F whole square, root over of that. So this is how you can write it. Relation between the resonant power and the off resonance power. So off resonance at resonance it is purely resistive. So resonant power is like this, V square by R, and any other frequency other than f0 is equal to I square R, and which is equal to V square by Z square into R. So if you do that, then you can write this at V square by R into this is Z square, so R square plus X square. And what is your X square? This is your uh, X is basically your omega L by omega C, isn't it? So that if we want to express in terms of Q, then how can we write Q here? What is given? The current in the series RLC circuit at resonant frequency F0 is maximum, that is quite we are aware of, so it is I0. Then power P0 is this, that is also okay, where XL is equal to XC, so it is purely resistive. At any other frequency either above or below f0, the power is what? It is I square into R, where I we should replace with V square by Z square, where Z is equal to what? Z is equal to R square plus omega L minus omega C whole square. So that is equal to Z, root over of that. So now if we write it here, we can write this as what is our Q? Q is equal to Q0 is equal to omega 0 L by C, that is equal to 1 by omega CR. Or what is equal to your usual Q apart from your resonance? It is basically omega L minus omega C, 1 by omega C into I divided by I into Z, isn't it? So it is reactive power and the total power. So then if or instantaneous power. So if these two are cancelled out, then you can write X in terms of, or rather this is not correct actually. I'll just go through it. I don't know whether it is, I don't feel it is correct. Okay. So we'll go through it later. So,
Sir, sir, I have
yes.
one question from the previous class. Sir, can you go to page number 94?
mm,
Yes, sir.
yes.
Sir, here, why are we taking omega naught is very, very greater than alpha? In
Omega,
the
oh,
third line on the right.
this one, no?
Yes,
This
sir.
is okay. So what is your alpha? It is R by 2L, right? This is the expression of alpha, and omega 0 is root over. So this is not always. There should be something connected, na? Anything, is it connected? Anything it is mentioned previously? No. So it is in the case when you take a value of say omega equal to L equal to say some millihenry, 1 millihenry, and C equal to 10 mu F, like that. So what will be your omega 0? It is 1 e power minus 3, then 10 into, isn't it? So root over of that. So we are left with what? It is 10, na? Am I correct? 1 by root over, if we take these values like this.
So it
So
will become 10 to the power 4 finally.
10, here it is square root, na? Here it is 10, 1 by it is 6. So okay.
10 to the
So it
power
is
4.
10 to the power 4. That radian per second. And if you look here, if R is around say your 25 ohm, and that if you divide by L, which is so You are getting what value?
1 millihenry.
No, this is 1 millihenry, and this expression alpha, so it is supposed to be, it is 500, so 12500, and here you are getting how much? No, I mean, in some situation, when you take parameters, say when resistance is going very low, in some cases where you have a very small resistance. So when we want a very selective circuit like this, we take our resistance to be low. So here, instead of that, if we take this resistance to be 1 ohm, then what will happen? That divided by 10 to the power minus 3. So you get 500. If you go lower than that, if you take only just connect R and L, only the varying resistance you are considering, then if it is zero point 0.1, then zero point 0.1 into 2 into this, so you are getting something, what you are getting, 0.05 into 10 cubes, so it is 50, which is much lower than this frequency. And if you select your capacitance even lower, 1 mu f or picofarad range, then for that also you are getting very very small, where omega your this thing, if it is picofarad, then what it is, it is something even higher, your omega. So then you can ignore this part, I mean your alpha square part you can
Yes,
uh,
sir.
ignore, and then you can write it like alpha plus omega 0, and another it is alpha 2 omega 2, and another is alpha minus omega 0, in that
So, sir, that is basically to like limit
way.
the bandwidth so that the
So
it
so
becomes
that
selective.
we can, if you get this kind of plot, and if you get a flat kind of plot, then you see, say for certain frequency, say at frequency equal to, which is your omega 0, you want your current, I mean you want to peak certain frequency out of a wide range, then you should design your circuit in such a way that it will amplify only those range, other than that it will be attenuated. So the signals which you have to pass in, that around that particular frequency you are allowing it to amplify, other than that you are trying to cut it off, you are not allowing it to enter. So then what will happen, we can select only what information we want at that particular frequency, isn't it?
Okay, sir.
Say
Thank you
our
so
signal is there for certain frequency, say some frequency f1, and that is part of with a noise which is at frequency f2, so which is a low frequency and this is a high frequency. If that is the case, then we should filter out other things, so we should take this, and other frequency we should ignore. So if you go apart from this frequency, then you see your current is going very low, so it is not, your circuit is not allowing to go through, allowing to pass through that particular frequency when you are exciting with a source of variable frequency. Okay, so it is having a lot of harmonic signals, so it may have one frequency, fundamental frequency, on top of that you have some other frequency omega 1, then omega 3, in that way lot of frequency rich signal is there. From that you want to pick up certain frequency and you have to ignore the noise, then you should go for this kind of design. So that is the main utility of learning this resonance circuit, and these are related with your filter design. Those who are from EC background, they'll be an electrical student also, they'll be going through in future, which are where you will find that you have to go for designing a filter. So it is like a band pass filter, or it's a very narrow band, huh? So for that particular frequency you will be, your signal will be amplified, and below that it will be attenuated, right? Anything else? Any other query, Harsh?
No, sir. No, sir.
Okay. Now we'll move to problem. It is solved. I'll ask you to go through because there is not much time left. So we'll go to the parallel resonance part. This part already was discussed. So you kindly go through the problem which are solved, and then if you cannot understand, then you can get me back. Okay. And now let us come to the parallel resonant circuit. So what happens when we take this kind of circuit where you have a RL and RC and you're exciting with a voltage V. So here this is the same voltage applied in the parallel path. So we'll take V as your reference phasor as we have seen, right? This, and then what will be your expression, your branch current? Your IC will be totally leading, right? This is your IC which will be leading, and if it is a practical capacitor, maybe with a high angle somewhere here. But in the ideal case, if it is an ideal capacitor, you will be having a 90-degree leading current. And for the RL part, there will be lagging current. So that is actually angle of lagging angle is phi L. So then when can resonance happen? During resonance, what happens? Your your net effective current will be in phase with your, this is your effective current, total current, which is your IC plus IL. The phasor sum of these two is your I. So this total current has to be in phase with your voltage, right? So it is behaving, overall expression over effect equivalent resistance will be purely resistive. So if that is the situation, then what happen? You should select your, if you have the RL and say you have to select your capacitance, or you have capacitance, you have to select your inductance. It will be in such a way that this component IL sine, this is phi L, IL sin phi L should be equal to your IC. Then only you can nullify, or you can balance the reactive component of the current. So if we can do that, then only parallel resonance is supposed to be achieved. So then it is this relation IC is equal to IL sin phi L, and IC is equal to what? IC equal to V by XC. Sin phi L is equal to what? It is XL by Z, and IL equal to V by Z. So if you substitute this, then what you get? V by Z into XL by Z is equal to V by XC. So if it is get cancelled, then you get Z square is equal to XL and XC. So what is your Z? This is your Z, R and L. This is R, this is L, this is capacitance. So this is your Z. So Z is equal to R square plus XL square. So if you substitute it here, and if you just put XL and XC, XC is equal to 1 by omega C, XL is equal to omega L. So that will cancel out. So now you are left with LC R square. Only the frequency part which is left, this is linked with XL square. So this is 2 pi F. Either you can write omega 0 square. So it is omega means it should turn out to be 1 by LC by R square and L square. Okay. So when your R is very, very small, then what happens? What happens to your resonant frequency? If R is very small, then your resonant frequency will be almost equal with your 1 by root over LC with your series resonance. Okay, like it is written. This is the resonant frequency and given in hertz if you express in terms of F. And if R is in ohm, L is in Henry, and C is in farad. Okay, so this is the expression of the parallel resonance. And now let us move forward. So what is the expression of the current as the parallel resonance, which is in phase with the voltage? So that is equal to IL cos phi L, isn't it? So now you know what is your Z, because this is IL equal to V by Z and R equal to, and cos phi equal to R by Z, and this is VR by Z square. So what is the expression of the Z? Z is equal to R square plus omega 0 square into L square. So we can write it as R square. Omega 0 square is this. So it will be L by sorry, L by C, if you express it over here, then it is minus R square, isn't it? Can you follow it? What is the expression of Z? So R will cancel out, so you're left with root over L by C. So that if you substitute instead of Z square, you write L by C, then you get the expression of your current which is in phase with voltage. So during resonance, your current is in phase with voltage, and it is having the expression which is equal to V by, or you can write V into RC divided by L. Okay, the ratio L by CR is known as the equivalent or dynamic impedance of the parallel circuit at resonance, and the impedance is resistive only. It is not actually impedance, we rather call it as resistance. Since current is minimum at resonance, your L by CR represent the maximum. L by CR is your resistance, so maximum impedance value of the circuit. So that is why it is called the rejector circuit. So when you're, if you plot like voltage, sorry, frequency, if you vary your frequency, then if you plot I, you will see your current will be minimum at resonant frequency omega 0, which is equal to this 1 by LC by R square by L square. Okay, so this is the case when you are getting a minimum current, and now with the tuning of the choice of your L, R, and C value, you can adjust the shape, so you can get this kind of shape. So it is a band rejector circuit. So during this band, you are getting a very low value of current, and for the other frequency, apart from that band, you are getting the signal amplified. So this resonance is known as the current resonance, because current circulating between the two branches is many times greater than the line current taken from the supply, and that is for sure, because this line loop current, this is your line current, which is your I, and this is your I, and this is your IL, and this is your IC. So we can find out the value of IL. What is your IL? That is equal to V by Z. So during resonance, Z is equal to root over L by C. So it is V into C by L. And what is your IC? IC is equal to V by XC. So which is equal to CV into omega. So which is equal to 1 by LC minus R square by L square. So these two value is totally different from the total current. I mean magnitude wise if we look at. Okay, so total current I is equal to sum of this, and that is supposed to be what we got it, which is equal to V into V into RC by L. Okay, so if we select the parameter as I have shown, we'll be seeing that when the parameters are given, when resonance is supposed to happen, then for different resistance value, if we take small, like the previous case, then we'll see that it will be, I mean narrow. Your band rejection will be for the small width of small range of the frequency. So in that case, you will see that this current value will be much lesser than these two, which are the loop current here. Okay, so that is why it is called the current resonance. Okay, so this is how it looks like as it is shown. So with the lower resistance we'll get a plot like this. If you can further reduce the resistance, it will come like this, and so on. This is the current waveform. This is your current, and This is your impedance. So we'll see that during resonance you will be having the maximum impedance, which is L by CR, and once you go in the higher zone your impedance will be capacitive in nature. Here it is purely resistive at the peak, and once you go lower frequency range it is inductive. Okay, so it is seen from the figure that impedance as resonance frequency is maximum, and that equals to this we have seen from here, because this is your I, so V by I is equal to L by RC. L by RC. Okay. And here the impedance become purely resistive. So it is practically resistance during parallel resonance. Okay, the impedance decreases and the current increases at the off resonant frequency. And the more lower the value of resistance you take, the this notch will be dominant. Okay. So this is again, I think, the repetitive thing. Okay, alternate method of showing calculation of resonance. So we have done through phasor algebra. You can do it with complex algebra, more or less same, but here you don't have to take the component, and in that way you don't have to solve. So what you are doing, alternating method is this. This is your what is your total admittance? Y equal to y1 plus y2, right? So y2 is this 1 by minus jxc. Minus is due to the nature, capacitive nature, and y1 is this. So from here you get your y1 and this is your y2. So if you add them up you get the effective admittance, which is this. And during the resonance it will be your admittance will be purely resistive, so this part has to be equal to 0. So from here we can solve it. That is to be the same as before. Okay, so this is the alternate approach. And whenever you'll be solving problem, then that time you can go using the phasor algebra method. You can go with like your complex algebra method, which one is convenient to you. And whenever I mentioned that whenever you'll be solving using this complex algebra, then always try to use the rake to pole command and vice versa in your calculator. So then, and then you put recall, then press F, then you will get the angle when you change from rect to pole, and the imaginary part when you change from pole to rect. So using this you can easily solve it. You don't have to do all those things, right? So you can do like that, and in calculator it will be in one step. You don't have to solve this when you will solve with the values. Okay. So this is the same way, it is written in a different way. I am not going through those things. Now let us come to the point where we take all three. We have not taken the other part. Is it taken somewhere? No. So the same thing we can solve. I'll just add a extra slide. So when you have a circuit like this is your voltage source V equal to Vm sine omega t, variable frequency. You have R1, you have L, you have R2, there you have C. So RL, RC, that is also possible. Then how can you get your resonance? This is your I, this is IL, this is IC. So phasor sum is equal to IL plus IC. Remember that here we are using KCL. Okay, and that is, if you draw the phasor diagram, if this is your voltage, that is reference phasor. So your capacitive current IC will be like this, your inductive current like this IL. Okay. So we need to find out the current, which is the phasor sum, and that has to be in phase. So then what are the condition? So if this is your phi L and if this is your phi C, what is your phi L? Phi L is equal to cos inverse R by ZL, which is equal to root over R square plus omega square L square. And phi C is equal to cos inverse uh, R by root over R square plus 1 by omega square C square. Okay. So during resonance, again, you have to resolve it in two part. One is this is your IL sine phi L, and this is your IC sine phi C. So that if you write, then you can write it in terms of IL sine phi L. What is your IL? It is V by root over ZL, that means R square plus omega square L square into this is cos. So sine will be omega L by root over R square omega square L square. And here this will be V by ZC, which is R square plus 1 by omega square C square, and sine phi C will be 1 by omega C into root over ZC, which is R square 1 by omega square C square. So V will cancelled out and we are left with what? Omega L by R square. This is R1, my mistake. This is R2, 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 R1, R1. So R1 square plus omega square L square is equal to R2 square omega square C square to 1 by omega C. So now uh, if we have to multiply it with omega square R square C square plus 1 is equal to, it will be omega C, isn't it, in the numerator? So this omega and this omega will cancel out. So we are left with what? Omega square L square R1 square divided by omega square R square C square plus 1 is equal to, this is R2 square. I'll just go to the next slide. So what we are left with, omega square, here it is L, there it is C, this is R1, omega square R2 square C square plus 1. So we can write, this is square actually, root over was not there. So we are L by C is equal to omega square L square plus R1 square by omega square R2 square C square plus 1. So from here we need to solve omega. So let us just, we have to cross multiply. So or we can solve it like this, omega square equal to, if we divide by 1 by L square. Anyway, if you solve it, let us solve it and we'll get the expression for omega. So from here we can find it out to be omega square R2 square C square CL or LC plus L by C is equal to omega square L square plus R1 square. So if you take omega square this side, it is R2 square LC minus L square this side is equal to R1 square minus L by C. So R2 square LC minus L square, and this side it is R1 square C by minus L into C. So your omega is equal to 1 by C into R1 square C by L, R2 square LC minus L square. Or we can take, this is the expression of omega square. So if you now take C common from here, so it is R1 square by L by C. And if you take 1 by LC, this C will cancelled out. And if you take 1 by, if you take LC common, then you're left with R2 square minus L by C. So if you can write omega 0 to be root over LC into R1 square and then R2 square minus L by C. So this is the expression of the parallel resonance when you have both RL and RC. So this is another expression. So at this particular frequency, now if you see that if we take R2 to be equal to 0, then what will be your expression? If you take R2 to be very, very small, then it will be 1 by LC. So this will be uh, uh, yeah, I think you can get back to your previous expression. What is your previous expression? This is 1 by LC into R square by L square. So if you take R2 to be very small, then you will be arriving at the same expression, right? Same as the before. So which is the more practical case? So what we have derived here, this expression for the parallel resonance is the more practical situation. Okay, so now if you plot with different, your um, frequency, variable frequency, if you plot the expression of the current, and then you will see that for different value of R1 and R2, if you take R1 and R2 very, very small, then again you will get a uh, like sharp notch. And if you take R1 big and R2 big, you will get a plot like this. It's the same way. Okay. So this is the expression of the parallel resonance when we have both the in the both the branch presence of R. Now let us come to the
Sir, one doubt.
hypothetical. Huh? Yes, repeat.
Yes, sir, one doubt. Uh,
Huh, huh.
sir, sir, in the rough work, sir, can you show the previous slide? Doubt is there, sir.
Here.
Yes, sir, the previous slide. Yes, sir. So here, sir, you have written phi L as cos inverse R1 by root over of that value. Yes, sir, that only. The rough work slide only,
No,
where you have.
actually there is a delay. I'll just do one thing. I'll close and reshare. Let's see then. Hmm.
Okay, sir.
Can you see now?
Sir, now it is. Acha, yes, sir, it's came. Sir, yes, in the final expression,
Hmm.
cos inverse R1 by root over of that value. Sir,
Hmm.
but in previous discussions, we were writing it differently. Like we were writing phi L as then cos inverse of I IL by IR. So that will be V by R1 divided by V by
This one,
that.
this one here.
No, sir. Sir, when we discuss in the starting classes, when we discussed about the parallel circuits of the thing, sir, in
Here,
that,
here. This is
sir,
the
what?
first slide for the parallel resonance, parallel AC circuit, parallel resonance. Can you see it?
Yes, sir.
Uh,
Sir, I'm saying that before the CA2 examination, when we initially discussed the
hmm.
parallel circuit, sir, there for finding the value of angles like phi as tan inverse of where you did that thing, sir, that you have written like IL by IR or that is V by. So, sir, it should be inverse. Like it should be cos inverse root over of r1 square plus omega square l square by r1.
No, no,
Because
no.
I write
Actually, if you have a phasor like this, your voltage phasor V, and you have a current phasor I, say it is a capacitive circuit, is leading. So this angle is equal to what? This is equal to phi. So it is IR. Here it is I into R plus phasor sum of I into, or rather we can write it, it is as V by R. This is I, and then this is your V by uh, and then this is your I think it depends on the parallel circuit and series circuit how you will want to draw. I'll just clear your confusion. So you have a
in the
circuit like
parallel
this.
circuit, we did it by like current, not by voltage for finding the value of voltage.
So if you have a resistive circuit like this, and then you have a inductor, another source, say it is capacitor, right? Like the previous case, this is your R1, this is your R2, this is your L, this is your C, or we can write it as XL, XC, the reactance. Then what will be the value of your this branch current I1 and I2? I1 is V remains the same, which is our reference phasor, right? This is your reference phasor V, which you are applying. So what is your I1? This is V by this Z1. So what is your Z1? This is root over R square plus XL square, right? So what will be your this I1 should be like this. This is your I1. So what will be the angle of this? This is your phi 1. So your if you just get the drop across I1 into R1, this is I1 R1, then J in 90 degree in that way, which is I1 into XL, then only you will be reaching here, which is your input voltage, right? This is your current. So I into R, this is your VR1. So VR1 here plus VXL1 will give you your total V. And again, this side also it is VR2 plus VXL XC2 will give you total voltage, isn't it? So then what will be the angle? This phi is equal to, we can write tan inverse XL by R, or if this is the whole thing, then I into Z1. So we can write it as cos inverse R by, this is the hypotenuse, this is the base. So R1 by Z1, and Z1 is equal to this. So that is why I wrote cos inverse R1 by root over R square plus XL square. Is it clear now? In the same way, if you have the capacitive circuit, if you have the capacitive part like this is your
No, sir.
I2.
One thing it is not clear, sir.
Continue.
Like for the tan inverse part, in the
Hmm.
tan we initially wrote, sir, IL by IR. So that will be
IL by IR. So I1 remains the same through this path. So
Acha, V is not constant, so that is why, sir. In the initial discussion, we took only R as in one branch and C in another branch. So that is why I think we wrote like that. Then V will get cancelled
parallel,
and
R and C were in parallel. R in one branch and C is in another branch, like that.
yes, sir, yes, sir.
Okay, so in
In
that
that we
case,
wrote
this is your voltage. This is your situation. You are asking like this. This is your I current.
yes,
This is your
yes, sir.
IR. This is your I C. Huh? So then what will happen? This is our reference phasor V. Your R will be in phase. So this is your IR. And what is your? It is purely capacitive. So your IC will be leading. So summation of these two will give you a total I current. So then this, if this is the angle phi, then tan will be what? Tan here it is
IC
I.
by I.
So it is IC into XC by IC into R. Okay. So it is XC by R, tan inverse of that. and that can be written as cos inverse of R by Z, when where Z is equal to your effective impedance. This is a parallel path totally. So effective impedance is what? It is, if we want to write admittance, Y is equal to R inverse plus J 1 by XC. No? It is actually minus 1 by minus J.
Here
Uh,
only, sir, here only. That is the thing which I am differencing with you. Sir, here only, if we write tan inverse, it will be tan inverse IC by IR, tan phi. Like phi is tan inverse of IC by IR, and IC is nothing but V by XC, and IR is V by R. So it will be like tan inverse of R by XC.
right. It is for here for this particular circuit. It will be it is tan inverse of IC divided by IR. So it is IC is equal to your V by XC divided by V by R. So tan inverse R by sorry, XC. And now if we just look like our complex algebra, that will just prove it. So this is through complex algebra. This is your R. This is your XC. So what is your overall impedance? It is a parallel combination of this and so it is 1 by R plus J into uh, it should be minus na here, so plus into 1 by XC. So then what will be your tan inverse that of, then tan will be equal to 1 by XC by 1 by R. So you can write it like V by XC by V by R, whatever the way you want to write. So you will ultimately get tan inverse R by XC. Okay. Now is it clear?
Yes, sir. Thank you, sir.
Okay. Okay. So here it is not R by X because this is series. This is not in parallel. Okay.
Yes, sir. Yes, sir. That was the. Thank you,
Hmm.
sir. Thank you, sir.
Hmm. Okay. So we are, I mean, let me complete it. Otherwise, it will take a lot of time to parallel resonance. We should not go forward with all those Q factor and all. Little bit is pending. So this is the case when we take the purely inductive, purely capacitive, and purely resistant, pure inductance, pure capacitance, pure resistance, as it is shown here. And when is resonance supposed to be happen? When your if it is a current source, then your, here we are driving it with current source, so this is your IL and this is your IC. So when your IL is equal and opposite to IC, you are supposed to get your parallel resonance. So we are writing in terms of susceptance, so it is 1 by JXL, which is minus J uh, 1 by omega L, and here it is J plus J omega C, so capacitive susceptance. So these two will be equal magnitude wise, then only we'll be able to find out, we'll be able to get the resonance. Like, so then what will your resonant frequency? It will be same as before, like here your B should be equal and opposite, so you will get 1 by omega L is equal to here also 1 by omega C. So this is in the resonance. So omega 0 is equal to root over 1 by root over LC, just like before. So you can see that your inductive susceptance is inversely proportional. It has become, it's just like the series resonance where your inductive susceptance is playing the role of the capacitive resistance, capacitive reactance, right? You can see this is 1 by omega L. So which was there in the series resonance, it's 1 by omega C, and just the other way down. So it is linearly increases with increase in the frequency. So we have just drawn it like this, and it will look like just as before, how we got our series resonance. Okay, so net susceptance is At resonance it will be like your it will be conductance. Actually it is 1 by r kind of thing. Okay, so whatever r value you are taking, 1 by that will be passing through. So the net admittance will be converted into conductance when resonance is supposed to happen at this frequency. So only thing is your I earlier your expression of I was like high, and here it is just the inverted. Initially for the series resonance your I was like this, but for the capacity the I mean RLC parallel resonance you'll get I like this, because you will be having the maximum value of the value of your overall admittance. So when your admittance is maximum, then you will have your minimum current. Okay, and if admittance is lower, then your current will be increasing. So this is how the expression look like. So if we want to write it, your expression will be R inverse plus uh, this is your net overall impedance. It is susceptance, so which is omega c by omega L. So if this is conductance, we can write it as something. Conductance is denoted by what? Usual symbol is, or I forgot actually. Anyway, so if we write it as C, C if we write it, there will be confusion. Admittance is denoted by Y usually. Susceptance is B. It is G, I think. So it is G plus this. Okay, so when this is not present, then G will be admittance will be minimum, and so on. So accordingly you will get your plot like this. Okay, so it is very similar to that of series RLC circuit, and with this we conclude our discussion. Whatever is there, if you cannot understand, just get back to me. We'll discuss in some other extra class, because tomorrow's class I would like to introduce to the elementary AC network theorem, which are same as DC theorem, like your Thevenin theorem, Norton theorem, and superposition theorem, maximum power transfer. Those things in terms of AC circuit will start from tomorrow. Okay, so with this we conclude today's class, and we are uh, left with only 3 more week to complete our syllabus. Okay, so there is not much time left for us, and we have to cover 2 chapters. So maybe